Right. So number 15 is where I've been asked to start. There we go, number 15. Before we even get too deeply into the question, I want you to look at the two-way table. What are they showing us in this far right column? The proportion, which we also call a what? Probability. We could call it probability. Yes, this is our claimed distribution. There we go. They're saying that in this district, these are the percentages of people registered as a Republican, registered as a Democrat, registered as a Green Party. I don't know if you guys are familiar with that at all, if you've talked about that in a government class or in another social studies class. Some states require you to register, some states don't, but a lot of people will choose to anyway, even if they're not required to. It oftentimes makes the check-in process when you go to vote a lot faster. It's like, what did you register as? They say this. Or when you go to vote in the primaries, you have to declare a party. And that's probably where this data has been pulled from. People that declared they were Republican, Democrat, Green, Reform, or other when they went to go vote in the primary. Because most states, you can only vote in the primary for the party that you have declared. So then they're looking at a general election, and they're comparing the way the votes were with this poll that they did of 400 voters surveyed right after they left the polling location. Now, when you go in for a general election, you don't have to tell anybody who you plan to vote for. You get the same ballot as everyone else. And so what they're trying to see is, did the way they declared before match up with what they actually ended up voting for? So we're going to do what type of a test here? Goodness of fit. Why is it going to be a goodness of fit? You're absolutely right. Claim distribution. So chi-squared, goodness of fit. So we're going to do state plan do conclude. I've gone ahead and labeled this as my claimed distribution. So when I write my null hypothesis, I can refer to that as just the claimed distribution because I very clearly indicated what I mean by that. So my null hypothesis here voters in this election voted according to the claimed distribution. And so then my alternative hypothesis would be that they did not vote according to the claimed distribution. And they didn't tell us, so what do you want to use as the alpha level? 0.05. Right, that's everything that I need in my state step. Then we get to the plan. This is where I name my test. I already decided that this is a chi-square goodness of fit test. And then we have to check our conditions. So we look at random first. Do I get random? Because it says random sample of 400 voters. All right, so there's my random. Do I need to check 10% here? Yes. Anytime we take a sample, we need to check our 10% condition. All right, they took a sample of 400 voters. So 400 has to be less than or equal to 10% of, they didn't say where they did this at, right? So as long as there's 4,000 people at this polling location, because they did take their entire sample from one polling location. So all voters at this polling location. Do you think it's a fair bet to say that they had at least 4,000 voters there? Yes. All right, so check off on that. Then I don't have normality. We have large counts. Remember, we're not looking for normal behavior. We're not looking for a normal shape. We're looking for what kind of a shape? Chi-square. All my counts have to be what? Larger than 5. All expected counts greater than 5. I need to make a table to check this. So I'm going to make a table similar to what they had here. How do I find my expected counts when it's a goodness of fit? We take the percentage that they give us, so this claim distribution. I'm not multiplying it by what was observed. We're multiplying it by the total sample taken, because I want to know if 48% people registered as Republican, what is 48% of my sample? Because that's how many I would expect to vote Republican. What is 43% of 400? Because that's how many Democrats I would expect to have here. We are going to label this table as expected counts. If you don't label your table, then they're not quite sure what you're looking at. So if you just said like C table at that point, label your table as the expected counts. Because some people also make a table then for all their chi-square values, those components, and so we want to make sure that they know what they're looking at. All right, so we have Republicans. We have Democrat. We have Green, Reform, and Other. What is 48% of 400? 192. So we would expect 192 people to vote Republican. What about 43% of 400? 172. Green Party was 4%. 16. Reform Party was 3%. 12. And Other would be 8. So here's my expected counts. All of my expected counts are greater than 5, so I can check that off. I've met all of my conditions. So then we get to the do step. So my chi-square test statistic is equal to the observed count minus the expected count squared divided by the expected count. What do you have to show in the do step? You have to show a picture. How many fractions should we have? We're going to have 5 fractions. Do I have to show all 5 fractions? You only have to show which ones? First and last. That is sufficient. All right, so chi-square observed number of Republicans was 197. Expected number of Republicans was 192. So 197 minus 192 squared over 192 plus, and then we go dot, dot, dot. And then I'm going to do my last one, which is the other party. We observed 6 and expected 8, so 6 minus 8 squared over 8. You do need to record all of the components that you have here so that if you have to do the follow-up analysis, you know which one is the largest component. So I got all right. So there's the components for a chi-square test statistic of 18.729. You do not have to take it out to 4 decimal places. I did, so that you guys can see this and compare. Take it out at least to 2 decimal places or 2 values after any leading zeros. So there's my chi-square. I need my picture and my p-value yet. My picture starts at 0. Remember, the big bump at the beginning and then a tail that trails off to the right. We're going to put 18.729 here. And so this shaded portion is what we are finding the probability of. We're finding that area. Chi-square with how many degrees of freedom? It's based on categories. How many categories do we have? 5 categories. So is it 5 degrees of freedom? 4 degrees of freedom. It's always -1. When we're doing goodness of fit, where we have 1 sample, 1 variable, it's number of categories -1. When we have a 2-way table where we've got a different number of samples and a different number of categories, we do rows -1 times columns -1. But when I'm doing goodness of fit, it's just number of categories -1. All right, then p-value. We do chi-square CDF, which is option 8 when you do second vars. Lower bound is 18.729. We're going to label that as our lower bound. Upper bound is something stupidly large, like, I don't know, 1 million. And then our degrees of freedom, which is 4 for this one. Pop that in the calculator. And it gives you what? 8.88 times 10 to the -4. Or if you wanted to write that out long ways, that would be 0.000888. All right, the only thing that we have left is our conclusion. Let's see if I can actually do this right now, because I'm going to have to bump down. All right. Are we going to need to do a follow-up analysis here? Yes, because we're going to reject. So the first thing I start my conclusion with, assuming the HO is true, hold on, let me get that written down first. Assuming the HO is true, what was our HO? Yes, voters in this election voted according to the claim distribution and then what? Assuming the hoe is true, I just explained what the hoe is. Yes, there's an 8.88 times 10 to the negative 4, or you can write it out long form, but you do need to reference your p-value here. Probability of getting chi-square of 18.729 or greater purely by chance. Because 8.88 times 10 to the negative 4 is less than 0.05. We reject HO. And what? There we go. Have convincing evidence that voters in this election did not vote according to the claimed distribution. And then my follow-up analysis here. The largest component of chi-square is what? 16. The largest component of chi-square is 16 because now we got to figure out where that 16 came from. So let's scroll back up and look. That was the third component, which would mean what? The Green Party. Let's go see how many people actually voted for the Green Party. Yes? Yes. So what we're looking for is proportionally what was expected versus what. So I'm looking at like 150% of what I expected is what actually voted for this, or only 75% of what I expected. I'm looking for the largest proportional difference. So that's a great question. I'm not just looking for which one is the farthest away, like absolute value-wise, but I want to know based on what I expected to happen. Do you guys remember back on last Tuesday? Last Tuesday? I think so, the PD day. When I gave you guys, no, it was SAT day. When you guys had the assignment that you had to complete on Canvas. Do you remember there was a question on there about like if I expected to find 50 bottle caps that were winners and I only found 40, would that be more surprising or less surprising than if I expected 500 and I actually got 490? Like, they're both 10 away. But the one that is like larger proportionally is if I expected 50 and I actually had 40. That's a larger proportional difference because that's 20% less than what I was expecting. The other one is 10 away, but I was expecting so many that 10 is kind of a drop in the bucket compared to what I expected versus what I got. Does that make a little bit more sense? Okay, good question. Great question. All right, so largest component of chi-square, because that's what this is telling me right here. This is telling me kind of proportionally which is the biggest piece, which is the farthest away proportionally from what I expected. Green Party, we expected 16. We actually had 32. So what was actually observed was double what I was expecting. So the voters for the Green Party were far larger than expected. All right. What other problems would you guys like to see? Yes. Yes, you may. 16B? Absolutely. All of 16, sure. Let's do 16 parts A and B. There you go. All right, if time permits. Which one? All right. Before I even go up and look at the top, there's something that jumps out at me here in part A so that I know what kind of test I'm going to be running. Difference. If we're looking for a difference, what kind of a test are we running? Homogeneity. That means I have two distinct populations or more. What are my two populations? Professional staff and the administrative support staff. So this is my population 1. This is my population 2. A test for homogeneity, I can have multiple populations. I could have more than just 2, but I will always have only one variable. What is the one variable here? Yep, drink brand preference. All right. It'll either be homogeneity or it will be independence. If you have a two-way table, so not just one column or one row of data, if you have only one column or one row, it's going to be a goodness of fit. And there has to be some kind of claimed distribution there. All right, so state. What would my null hypothesis be? Yes, there is no difference in drink brand preference for professional and admin support staff. And so my ha would be that there is a difference. Alpha level, 0.05. I'm going to go ahead and do my expected counts right now because I've got some room off to the side here. I'm going to need a two-way table. Yes, you have to have your expected counts displayed somewhere. Good question. You can absolutely put it right next to their table. That would not be a problem. As long as you have the table labeled expected counts, you are good no matter where you put it on the page. All right, so we have our professional staff. Oh, I'm going to put that up on the top, not on the side here. Professional staff. We have our admin support staff. We have Coke and Pepsi. How do we find the expected counts? Yes. So for this first box here, we're going to multiply 44 times 22 divided by 95. And 44 times 22 divided by 95 gives me about 10.89. $10.189, yes. Thank you. So the remainder of my expected counts, 33.811 for admin support staff and Coke, 18.811 for professional staff and Pepsi, and 39.189 for admin support staff and Pepsi. So now we get to our plan step. Because it said we're looking for a difference in, we said that we know this is a chi-square test for homogeneity. And then we check our conditions. How many samples were taken? 2 samples. So we have to check random for both samples. And if required, we have to check 10% for both samples. Do we get random for both of these? Yes. It says simple random samples of both. So simple random sample, you can abbreviate that SRS if you do not want to write out simple random sample. So that's enough to check the random condition for both populations there. Independence 10% condition, we have to check both of our samples. How many professional staff were surveyed? 22. So 22 needs to be less than 10% of all professional staff. So as long as there's 220 professional staff, we are all good there. And how many admin support staff? 73. So 73 has to be less than or equal to 10% of all admin support staff. So there has to be at least 730 admin support staff. It says this is a large company, so I feel like those are safe assumptions to make. And then we check our large counts. Are all of the expected counts 5 or larger? Yes. And I'm going to put a note here, see table. All right, now we get to do. So chi-squared is equal to the sum of observed minus expected squared over expected. So my first fraction, we observed 14 professional staff that preferred Coca-Cola. We expected 10.189. Plus dot, dot, dot. And then do my last one. We observed 43 of the admin support staff preferring Pepsi. We expected 39.189. So the components of my chi-square test statistic got 1.4254 plus 1.2297 plus 0.4296 plus 0.3706 for a total chi-square test statistic of 3.4553. Just given what we know so far, what we've seen on other tests that we've run, before I even find my p-value, do you suspect this will be a reject or fail to reject?
Reject.
I think this is going to be a fail to reject. Our test statistic is not even 4. It's not even 3.5. It all depends on my degrees of freedom, how that affects my distribution. Let's go ahead and calculate the p-value. So we do chi-square CDF, 3.4553. If you guys at least do 2 decimal places, that's plenty. When I did my answer key, I did 4. Upper bound enormous. How many degrees of freedom should we have? 1 degree of freedom. For my degrees of freedom, we do number of rows, which was 2 minus 1, times number of columns, which was 2 minus 1. So I have 1 times 1. That's why we have 1 degree of freedom. Yeah. What kind of a p-value do we get? Yes. 0.06305. You can go on if you want. This is enough right here for me to tell whether we're going to reject or fail to reject. I still need to draw my picture. So it's 0, big bump here, and then a tail off to the side. Chi-square with 1 degree of freedom. My test statistic, 3.4553. So I made the shaded area the size that I did based on my p-value. This should be the percentage of the picture that's shaded. So that's why I did that. You could absolutely have it farther over, but your p-value is telling you how much of the area under the curve should be shaded in. Yep, good question. All right, let's extend this down so that we can do our conclusion. I'm going to abbreviate this a lot so that we definitely have time for part B. Oh, sorry, zoomed in too much. Assuming HO is true, no difference. I would write this out a lot nicer if I was doing this on a test. Assuming HO is true, there is no difference between these two groups. There is a 0.063 probability of getting a chi-square test statistic of 3.4553 or greater purely by chance. Because 0.063 is greater than 0.05. We fail to reject the null. And do not find convincing evidence. Of a difference. Do I need to do a follow-up analysis?
No.
No, because we failed to reject. I do not need to talk about the largest component of chi-square. Also, if you look at the components of chi-square, they're all pretty small. These were not very far away from my expected values. All right, part B. Part B says that we had 6 other professional staff members who didn't complete the survey. And I want to know if they had completed the survey, would that change our conclusion at all? So we're going to make 2 extreme assumptions, and we're going to see if either of those extremes would lead to a different conclusion. So the first thing that we are going to assume is that all 6 chose Coca-Cola. So then my observed Coke and Pepsi, professional and admin. If all 6 of them chose Coca-Cola, then there would be 20 here. And all the other numbers would stay the same. So then I would have 28 total in my professional staff, still 73 here. I would have 50 for my total Coca-Cola and 51 for my total Pepsi. That one would remain unchanged. This is everyone chooses Coke. Or all 6 choose Coke. Don't have a ton of time left. So the other one that I would do is assuming they all chose Pepsi. If every one of those professional support staff person chose Pepsi, I would have 14 here and 14 here. Admin would remain unchanged, 30 and 43. So I still have a total of 28 in my professional, still have 73 for my admin, 44 choosing Coke, and 57 choosing Pepsi. I would make 2 more tables for this. What are my expected counts if all 6 chose Coke? What are my expected counts if all 6 chose Pepsi? And I would run a chi-square again and find a p-value again. I don't have to do the whole formal thing. I can do this all just in my calculator, because they didn't ask me to rerun the whole test for them here, but that's what I would need to do. If all 6 of them chose Coke, my chi-square test statistic, instead of being 3 point something, would go to 7.4 something. That changes my p-value now to 0.006. So I would reject if all 6 chose Coke. If all 6 chose Pepsi, my chi-square would only be 0.65. So my p-value there would be 0.419. I would still fail to reject if all 6 chose Pepsi. But if all 6 chose Coke, we would change our conclusion to reject instead of fail to reject. If you guys want to see the level of work that I would expect on a part B like this, if you were to take the test, hop in and check out my answer key. That has what I would expect to see. It's got 4 tables on there, the chi-square values and the p-values, along with my new conclusion.